Hi guys, in the first part of this lecture we talked about the classification of solid and semiconductors, metals and insulators. In this part we're going to talk about the band structure, which is another way of talking about energy bands in semiconductors, which gives us a little bit more information. So to fully understand the behavior of carriers in optoelectronic devices, we must have access to the band structure. So thus far we have been talking about band diagrams, which represent the energy bands in terms of energy. So you have diagrams like these ones, where you have the valence band, the conduction band, and so forth. And sometimes the energy is plotted as a function of spatial coordinates, such as x, but this only gives us information regarding energy. Okay, the band structure, as opposed to the band diagram, sometimes called the EK diagram, is a graph or a plot of the allowed energy states E energies as a function of the corresponding wave vector. So you have a graph of the energy as a function of the wave vector K, which we're going to talk a little bit more about K in a little bit. So to understand the EK or the band structure, it's usually easier if we start out by talking about the behavior of an electron in a one-dimensional periodic lattice. So let's say that you have atoms periodically arranged along only one direction, like this. Okay, let's say X. And in order to understand the band structure of three-dimensional lattice, it's usually easier if we start out by talking about 1D periodic lattice first. So the atoms are arranged along one direction only. It's useful for us to look at the band structure of this type of lattice first. So let's take first just one isolated atom, okay? And let's consider the potential energy due to the nucleus of this atom as seen by an electron at a distance r away from this atom. Well, the potential energy that is going to be associated with the electron is going to be given by this. So don't be confused by the V here. This is not electrostatic potential. This is potential energy as a function of the distance r is equal to minus E squared, where E is the elementary charge, over 4 pi epsilon naught times r. So it's proportional to 1 over r, and there's this minus sign over here. So it's minus a constant times 1 over r, which will give us a function that rises up like this, okay? And if you consider the symmetry on the other side, you would have the same thing. So let's say that on this axis you have potential energy as a function of r. Now if on the other hand, on this axis you have one-dimensional lattice, so let's consider that this dimension is x. We can replace r with x and we get this right here, okay? So this is what you get for one atom. Now if you have a periodic, one-dimensional periodic lattice of atoms, you're going to have more atoms, like so, and associated with each of these atoms, you're going to have the same potential. So the red dashed curve is going to be repeated for each atom here, and so on. So the actual potential energy is going to be the sum of all of these curves. This is better illustrated here, okay? So you have the red curves, the nuclei of the atoms, and the potential energy that the electron is going to see is the sum of the dashed red curves, which is the the gray curve right here. And since the lattice is periodic with the period A, let's say, which is the distance between atoms, the potential energy is going to be periodic with the same period. So the gray curve has the same period as the pitch between atoms. For the periodic structure, therefore, each atom will produce a potential energy distribution around its center, exactly like the one we've just shown. And the total potential energy, V dash, of R is the sum of the potential energy due to all the atoms. Okay, so it's also periodic, like we've shown here. Now we can find the wave functions and associated eigenenergies of the electrons in this lattice by solving the time-independent Schrodinger equation subjected to this periodic potential, which is plugged in right here. So this is just the time-independent Schrodinger equation with this periodic potential energy function. Now, as we've said, the interest in this problem is because most of the semiconductors we're going to look at are crystalline. So they will also have a periodic lattice, a three-dimensional periodic lattice, and the resulting band structure is going to be a little bit more complex, but the basic ideas are going to be the same. But so far we're looking at a lattice that's one-dimensional. Okay, and if the potential energy function is periodic with the same periodicity as the lattice, we can use the following theorem postulated by Felix Bloch. Okay, so he demonstrated that if the potential energy is periodic, the probability of finding the electron, the absolute value squared of psi, is also periodic. And therefore the wave function psi associated with wave vector k, so psi of k at position r, is going to be given by the product of a periodic function, which is this u of k here, which is, let's say it's a periodic function. So the electron is subjected to the potential energy, which is periodic. The wave function is going to be given by this. The product of a periodic function times this term here, which in phasor form corresponds to a plane wave, right? Those of us that have studied electrodynamics might remember that if you have three-dimensional space, let's say Cartesian coordinates, and you have a wave which is propagating at any given direction, okay, in space, a plane wave, this plane wave might be described in phasor form by an amplitude times e raised to the power of minus j, e raised to the power of minus j k dot r. So if the wave is mathematically described by this, it means that it's propagating in the direction of the wave vector k in space. And if you take a plane which is perpendicular to this propagation direction, the phase is going to be constant along this plane. So this is a constant phase plane perpendicular to the propagation direction. So this describes a plane wave. And therefore this term right here describes a plane wave with an amplitude of 1, but a plane wave associated with a wave propagating in the direction of k. Okay, so k is the wave vector. And, well, that's it. So if the potential energy is periodic, the wave function is going to be given by this, therefore. Okay, the product of a periodic function u of k times a term that's relative to a plane wave. So the wave function is a product of a plane wave in a periodic function. In a one-dimensional lattice, the periodic function is such that u of k at position r is equal to u of k at position r plus a. So this is the period right here, and this just states the fact that the function u is periodic with a period a. Okay, so what we just said. Furthermore, the energy values for the wave functions are going to be periodic with respect to k as well. So if you make a graph of the energy eigenvalues or the eigenenergy as a function of the wave vector k, or actually this is the magnitude of the wave vector k. So this is the wave vector k, this is just the magnitude. But if you make a graph of E versus k, the curves are going to be periodic with respect to k. So you're going to, for a one-dimensional lattice, you're going to obtain graphs similar to these ones right here. So you have, let's take this curve right here. It's periodic with respect to k, and the period is 2 pi over a. Okay, the period of the lattice is a, so in k space, the period is going to be 2 pi over a. Besides, as you can see in this graph, you will also observe the energy bands here. Because if you just look at the energies, you can see that you have energy values that the electrons can assume, right? But you also have energy values that the electrons cannot assume. So the way to look at the band structure is that each point here represents a wave vector k that the electron can assume, and the corresponding energy associated with that electron. So in this state, the electron is going to have a wave vector k, and the corresponding energy is going to be this one right here. Well, the energy is periodic with k. The band structure is obtained by solving Schrodinger's equation subjected to the periodic potential, be it in one dimension or 3 dimensions as well. There are different numerical and analytical techniques for solving this in one dimension, approximations that can also be used in 3D. And for most materials of interest, the curves are available in the literature. So the main points regarding our previous discussion on the band structure is that each allowed discrete energy level is going to correspond to a discrete allowed wave vector. So what we just said, each point in these curves corresponds to an allowed state with corresponding k value, which you can read in the x-axis, and energy value that you can read in the y-axis. Also notice that the probability density function behaves like a wave. We can get this from the fact that we said that the psi function or the wave function is going to be the product of a periodic function and this term right here, which represents a wave, a plane wave, okay, propagating in direction k of the wave vector k. So the probability density function behaves like a wave. The curves shown in the EK diagram are not really continuous, but rather you have discrete points in each curve of the order of 10 to the 23, as we saw before, which is the amount of energy levels per band. If you look at one period, let's say from here, minus pi over a to pi over a, you're going to have of the order of 10 to the 22nd to 10 to the 23 points composing this curve right here. So it's not really continuous, but a bunch of points, discrete points, which are really close to each other, since you have 10 to the 23 points. Also, in the band structure, you can notice that there can be energy values which cannot be accessed by the electron. Okay, so the electron can be in states associated with these points with corresponding energy and k values right here. But notice that in this interval here, there are no states, there are no allowed energy or wave vectors that the electron can assume. So this right here would correspond to the forbidden band. If, for example, this was the valence band and this was the conduction band. So what we've just seen is the periodic zone picture of the band structure, okay, which for a given range shows E for all values of k, perhaps showing many periods. But due to being periodic with respect to k, this picture has redundant information. It would be possible to just show one period, okay? So this is what's called the reduced zone picture, where you would show only one period of the band structure, all right? So it would look something like this. you would show, since for a one-dimensional lattice, one period corresponds to 2 pi over A, you would typically show the band structure with K ranging from minus pi over A to pi over A only. Okay, so all the information is here. If you repeat this over to either side many times, you will get the periodic zone picture, but it would have redundant information. So if you show things as a function of K, wave vector K, we usually say that we are working in the K space, okay? And also we can talk about the Brillouin zone, which is exactly this. The zone corresponding to one period in K space is the Brillouin zone. So this range right here. The third picture is the extended zone picture, where the bands do not overlap with respect to K. For the band structure that we've been looking at, the extended zone picture would look something like this, okay? So instead of showing, for example, considering this band right here, instead of showing this part here, which overlaps with the lower band in K space, we would show this part. But notice that since it's periodic, we would still have all the information that was in the center here, because it repeats itself here and here. So there's no loss of information. It's only displaced to the side here so that it doesn't overlap. It's just an alternative way of showing things. So the same thing in this band here. Instead of showing this portion right here, you show it right here so that there's no overlap with the bands below or above it. Okay. To summarize, the bands in the EK diagram or band structure are the same as the bands shown in the band diagram. The band structure has additional information, so you can see the allowed K values, okay, where K is the magnitude of the wave vector K. So it implies the wave nature of the wave function, but also K is associated with the linear momentum of the electron. So the electron, in a sense, behaves like a wave, but if you want to find the momentum of it, we're going to see that the K has an association with that as well, and that information you can get from the band structure. Okay. Also, the highest completely filled band in the band structure is still the valence band, and the lowest vacant band is also associated with the conduction band right here. Okay, so if we go back to the band structure, looking at the reduced zone picture, let's say that this band was the lowest one that was completely empty, so this would correspond to the conduction band, and you could, right beside this diagram, draw the band diagram right here, and this would be the conduction band. That would mean that this band right here would be the valence band and would be the highest one, which is completely filled, right? This one is the lowest one that's completely empty. This would need to be the highest one, which is completely filled, and therefore it would be the valence band. So all the states here would be filled with electrons. And you would also have an energy gap, a band gap right here. So this might be the band structure of a semiconductor if this were in the range of 1 to 3 electron volts, for example, right? But there's a direct correspondence between the band structure and the band diagram. That's what the main point is right here, okay? So finally, in real materials, the lattice is somewhat more complex because it's three-dimensional. So the periodicity for example, in a diamond lattice is not as simple as the 1D periodicity that we just saw. And the band structure, accordingly, is going to be more complex as well. Okay. In this case, the band structure is also periodic in K, so this remains true. Periodicity in K still takes place, and you also see allowed and forbidden energy values, but the bands themselves, although periodic, may look somewhat more complex. Just to give an example, this would be the band structure or part of the band structure for silicon. So you see that the bands here have much more complex geometries, but they are periodic as well. Also, there are a few more details here. You might ask, what are these gamma, X, W, and K points right here? So this would correspond to the K space. Well, as opposed to one-dimensional lattice, for a three-dimensional lattice, the K space or the wave vector space is going to be three-dimensional. So you have, instead of being just a line, it's going to be an actual three-dimensional space of points. And if you want to plot the band structure or the energy values corresponding to different K values, you would need to have a four-dimensional graph, right? Where you would plot the fourth dimension would be energy, and the other three dimensions would be the three directions that you can have associated with the K vector. Well, this is not practical, and in reality, what is done is in the K space, or in the space associated with the wave vector, different paths are chosen along given directions in the K space, and these points here, gamma, X, and W, and so on, correspond to points in the K space. So the band structure follow paths along these lines going from one point to the next in K space. So this is an additional complexity, but we don't have to worry too much about this. All we have to know is that the band structure is still periodic, and it still shows the energy levels and the associated K values for the different bands. And as you can see here, we could very easily define a forbidden band from around this energy right here down to this energy right here, where we can see that there are no states available in this region. So that's the kind of information that we're most interested in when looking at the band structure. Okay, so on our next lecture, we're going to continue to talk a little bit about the band structure and perhaps go on to define the density of states. Okay, so thanks very much for your attention, and I'll see you around.